Welcome to Reliability Matters, a podcast for the electronic assembly industry. Each episode covers topics related to reliability, best practices, and environmentally responsible assembly techniques, with insights from experts across the electronic assembly industry. Now, here's your host, Mike Conrad.
Welcome back to another episode of Reliability Matters. I don't know if I can ever get that music out of my head. I've listened to it too many times. It's been quite some time since we've talked about thermal profiling, and there are, obviously everyone knows the importance of a proper reflow profile. I was involved in producing a study with some colleagues over the correlation between thermal reflow temperature, particularly peak temperature, and contamination on a board. It turns out that if there's just a minor drop, just within 3 or 4% of the peak temperature, we end up with a lot of extra contamination on a circuit board. And that fact just reminded me that it's probably a good time to talk again about thermal profiling. And who better to do that with than our friends over at ECD. So I would like to introduce Mark Waterman from ECD. Welcome, Mark. Thanks for agreeing to be on the show.
Yeah, absolutely. Thanks for having me.
Of course. So tell me a little bit of, not that I can't imagine there's too many members of our audience that have never heard of ECD, but for those that don't know about ECD, tell me a little bit about ECD, its background, when it started, what you guys are known for.
Well, ECD was actually started in 1964. We've been around for a few years. We started in the medical device manufacturing arena, and because of quality concerns, we got into contract manufacturing, circuit board production, and really the whole soup to nuts manufacturing of medical devices, which required quality tools. So we invented electronics to measure different processes that we were using, including the MAUI thermal profiler. That was introduced back in the early 90s, late 80s. And we've been measuring thermal processes ever since. We have tools for not only measuring product reflow profiles and wave solder profiles, but also to do machine quality management with rider pallets for every type of heating or soldering process that you can imagine in electronic manufacturing.
Excellent. I saw, well, let me throw this on the screen. I saw that you recently dug up a old product of yours. This was a 25-year-old mole.
Yeah, we had a contest for, who's got the oldest mole. And we found one that was back in the 90s, still functioning. Unfortunately, there's still some of those out there, and we try to get them upgraded to newer product. But some of those things are just tanks, and old through-hole technology never fails.
Yeah, right. Sometimes we come across some of our old machines. We've been building cleaning equipment since 92, so going on 30 years. And I cringe when I see some of the older machines because, they're still working. There's nothing wrong with them. They don't look pretty anymore. The paint's all gone, and there's probably a few drips coming out of the chamber here and there, but they're usually sitting on some kind of containment, water tray or something. But some of them are still running. So if someone has a very old profiler that that 25-year-old profiler, assuming it's still working, there's two ways to build a product. There's two goals when you build a product. One is to make it last a long time. That's hard, but it's possible. And the other is to make it relevant for a long time, which is probably even more difficult than making it last a long time. So if someone has an old mole, if they go to some used equipment place or they buy it at auction for $22 or whatever, at what point does it lose its relevance? So, how does it stay relevant? Does it not stay relevant?
Yeah, unfortunately, like say, some of those older moles, even though they might still be functional, the software that is used to communicate with them goes obsolete. Microsoft kind of ensures that for us, unfortunately. Time does march on, and so that original profiler The software came on floppy disks, so even if it would run on a normal Windows machine, you probably don't have a floppy disk to install it. So that's how far we've come in software. The original, some of our original equipment had serial outputs to little thermal printers to print out the profiles, and now, like I say, we're in the modern age, and if you don't have a Windows machine and something that's compatible with the latest operating system, the products don't work anymore. So that's the unfortunate reality, is that we are software based. So we do our data analysis in software, and if Microsoft makes changes to the operating systems, we need to make updates to our software, and sometimes that can't be backwards compatible with older equipment. So.
Yeah, we've had the same challenges where the computers are lasting, the hard drives are working, the power supplies are working, the touchscreens are working, but the software breaks. And not only when they come up with a new version of Windows, when they come up with a new service pack, when they come up with an update, we usually recommend our customers turn off their auto updates, because every once in a while it'll auto break, and
yeah, exactly.
And I don't know, maybe we're just not in the right group. We're not hanging with the cool kids, but we don't know when they're going to do this, and we don't know it's going to break until it breaks, right? That's just the nature of Microsoft, I suppose.
Exactly. We've got some fixtures from some of those original moles. We've got a laptop that's in our lab that runs DOS off a floppy disk.
Wow.
We use for a firmware fixture, and we just look at that every time we have a power failure. We wonder if it's going to come back, but it's got to be a 20-year-old laptop, and it still runs. The display comes up, it does what it needs to do, and it might be old, but it's functional. So it's.
So I've often wondered, Mark, there's the oven guys, there's oven manufacturers that build the ovens, and then there's the thermal management people that, like you, that basically tell the user how the oven's doing relative to their board. How come that's not all one product? What has stopped Heller and BTU and all the other companies from basically stomping all you guys out of business by just creating their own profiler? Why are there two entities there?
Yeah, and it's expertise and subject matter experts. The oven guys are great at heating things up and making a reliable system. Reflow ovens have become extremely good over the last couple decades. They're reliable. They heat evenly. They do a really good job at what they're meant to do. But the deeper analysis that's required software-wise, it takes a little more expertise than controlling the temperature of a zone. Coming up with the recipe, doing some of that automation, and some of these big guys, we're starting to play in each other's sandboxes, right? We are crossing boundaries of traditional. You do this and we do that, and that's okay. There's still, I think, plenty of market share for everybody, and I think they will always be better at creating ovens, and we'll always be better at profiling. We need to continuously innovate and provide better value than our competitors. So that keeps everybody innovating, improving, and improves the value that the customer gets ultimately.
Yeah, I guess I could have asked the question in the opposite too. I could have said, "How come you guys aren't making ovens? You're already measuring the output of an oven. Why not make an oven?" But I understand there's a core competency there, and the skill sets required to build a conveyor to control temperature as precisely as they do are probably completely different skills as writing code to interpret all that energy and forecast it. So let's say I'm brand new to profiling. I just graduated college. I've been parachuted into J-Bill or something, and now and I've been charged with updating our company's profilers. What do I need to know? What is a good foundation to start off with when it comes to choosing a profiler or choosing to profile at all?
Well, that's one of the major problems in the industry is apathy, right? If we don't have to do it, let's not do it. You could probably run into the same thing with cleaning, right?
Sure, absolutely.
So overcoming that apathy is, build it into a quality program and define what is good quality. Managing all your thermal processes requires that you measure them to manage them. And you need to have a quality program that includes that. The frequency can be determined and flexible. The amount of changeover that you want to tolerate and can be adaptable. But you need to document, have it in your quality program, and then follow it. As engineering resources and manufacturing resources become smaller and smaller, the need to profile hasn't been reduced. It's actually increased. The smaller assemblies, we have different types of chemistries now with low temperature solders and some of the new sintering technologies. These process windows are getting smaller, not larger, and the need for profiling just increases. And at the same time, automation marches forward, and they want to be able to do this faster, easier, defer it or transfer it to operators instead of engineers. And so the software has to, and the systems have to become simpler to use, more intuitive, and give you better insight. So make it less complicated, but give me more information.
Sure.
So it's quite a challenge. And that, like say, the engineer that you just dropped in that doesn't know anything, they need to have a process on what they need to measure, how often do they need to measure it, and what are the bumpers that I need to be aware of and be monitoring to make sure I'm successful.
So let's talk about that a little bit. You talk about how often do I need to measure? So if, in our world, in the opening, I talked about a study that we were involved in where we were reflowing boards at a quote unquote proper peak temperature, 250 degrees, and then extracting contamination from under various parts of the board and determining that, we had basically a pass. The contamination level was fairly low with this no clean flux. And then we reflowed more boards, identical boards, with the peak temperature being off by 10 degrees, which was 4%. And then we did the same extraction on chromatography, and we had increases in contamination up to 600%. So 200%, 130%, 180%, up to 600% across the board. And that peak temperature turns out, is really important to hit. And in my understanding, and this is probably a human nature thing, not specific to profiling, we tend to set up a profile with perfect conditions, with perfect boards, with the best operators, ideal conditions. Everything's been calibrated. All the vents on the reflow oven have been cleaned out. Everything's working good. And then we get our perfect profile, and then we, leave, go to the bar, go party, go to Tahiti, whatever. And all of that just very slowly starts to drift, and we don't go back and check it until we see a problem like contamination or whatever other solderability issues maybe. How often should someone recheck their profile? Is this a daily thing, like when you start up? Is this a monthly thing, a quarterly thing, or do we just respond when things break?
Well, that would be the apathetic part. Usually people don't check their profile until a problem's already happened. So they're in risk management mode. They're trying to stop the bleeding. And that's really in a manufacturing for quality anyway. You want to have a recursive, I want to do a check on this. And it sounds a little snarky, but you could check it as often as you can afford to make bad boards for. So if you're making bad product for a month and you can afford that amount of risk, then check your profile once a month. If you want to make bad boards for a year and absorb that risk, then check your profile once a year. I'm not risk tolerant, so I would do it a little more frequently, daily or weekly. And it depends what you're making. If you're making Bluetooth earpieces that you expect to be out in the field for 18 months and then thrown away, it's a lot different than an analog brake controller that's going on a school bus or something, right? So it's all about managing the risk and the exposure to risk that you might have. I know now that more and more electronics are going into active safety systems for for the automotive industry, more and more medical devices, the amount of liability has really increased. And having a quality system where you're measuring it and proving that your process is stable and in control is more and more important than ever. So,
yeah, that makes a lot of sense. So me still being the new guy, we'll keep playing this role
okay, sure.
in thermal profiling. What are the most common mistakes I'm going to make based on your experience?
Understanding the importance of the profile itself. So, just as you mentioned with the cleaning, different alloys and fluxes require different types of values to monitor or measurements to monitor. Same with voiding. So you need to be aware of what the failure modes might be and what can mitigate those. Also, the points to measure as we get into larger BGAs or more complex assemblies. We need to not just measure a solder sample with isn't populated. You're not getting real thermal data from that, which is, if you want to have a quality product, you need to start off with a sacrificial board that's populated. Then it might cost you $300, and that's the cost of quality. We need to factor that into our quality system, is that we need a populated board to profile. Thermocouple attachment has always been an issue. There's the trade-off between fast and easy and difficult and good. And
I think that's a life lesson in general, right? Not just, not just for profiling. So let's drill down on that one, because that one I hear a lot. Again, I'm not an expert in profiling, but what little I know, it always talks about the bonding of the thermocouple to the board. Can people use capped-on tape? Can they use a foil tape? Can they use glue? I mean, what shouldn't they use? Let's start with that.
The worst offender is capped-on tape. I mean, capped-on tape can be used as strain relief. It's not good for anything else in profiling. Maybe
right.
to hold something down.
Why not? I'm just curious. I mean, it has the ability. Does it have the ability to hold it down, or does it affect somehow the
it doesn't conform very well. It likes to keep its shape, so it allows air in underneath it,
okay.
and it influences the measurement.
Okay, so instead of measuring the actual surface of the board at that point, you're measuring the air a few microns above the board.
Correct.
Okay,
and swirling around it. And we'll get into this. Some of this is opinion, and there are many opinions out there. But foil tape is probably the second worst. I mean, it is fast. It is convenient. It conforms around the thermocouple bead, so it reveals its shape, or witnesses it, so you can see where the bead is. The silicone adhesive that is used starts to soften right around 220 C. So right at the most important part of your profile, the glue starts to give out, and may lift, it may not. It's good for a couple runs. If you need to get some quick data or a confirmation run, it's not as repeatable as other methods. So it is fast and convenient. Repeatability leaves a little bit to be desired. So if you need to do more than 2 or 3 runs, it's probably not appropriate. Again, if you can use the capped-on tape to strain relief the wire so it doesn't pull out, and you can use the window painting method to put on the aluminum tape, and you'll get 2 to 3 runs. SMT adhesives and epoxies are nice. You can put on a very small amount so it doesn't influence the reading, either as an insulator or as a mass. It also takes curing time. So it may take 24 hours to cure, or you may have to have some UV light source to instantly cure it. And it's good repeatability-wise for many runs. The best attachment method, the most thermally intimate and repeatable method, is high-temp solder. And most of those are leaded, which is a concern for some lead-free houses. There is a RoHS exemption for high-temperature solder use for thermocouple attachment. So you're still in compliance even if you use it.
Well, because in theory, after you get your profile, you desolder it, right? So the board is not going out with lead in it. It's only
right.
there for a moment. basically.
And again, we asked for a sacrificial board, right? This should never make it out into the wild, so to speak, and
Oh,
into the
okay.
population. So it's a measurement platform. If you do need to use it and send it to a customer, there are other ways to do that are non-destructive. But again, there's pros and cons to that. So the high temperature solder is the best way. Again, you want to limit the mass of the attachment, right? Because you want to measure the solder joint, not a big blob of solder that you put on there. So some care has to be taken. And thermocouples are difficult to solder. You need a little bit of silver in with your SN5 or SN10. You should use a really aggressive flux. I have a secret weapon. It's Johnson's J35. Really nasty stuff. Don't get it on your hands or your clothes. It'll eat through it, but it works really well on thermocouples. So there's your secret tip for the day.
What type of thermocouples are recommended?
Type K is the most common.
Mm-hmm.
It's readily available from many manufacturers. It has fairly good repeatability. It's accurate to 2 degrees, 1.1 degrees C, 2 degrees F kind of stuff. It's got a little bit of chrome in it, so they don't rust or wear out. So they have fairly long life. The biggest thing now is the process temperatures are getting up above the threshold for Teflon insulation. So the glass insulation tends to fray and wear out a little bit faster, and some people are a little disappointed with the lifespan of the thermocouple now, but they are consumable. It's just the cost of profiling.
Well, I would imagine they take a beating with the attachment and unattachment, detachment, when they're bonded, they're removed, and that's got to take a toll on them as well, right? And they're being bent, and you probably get some metal fatigue over the years or over the months,
yeah, the insulation gives up way before the wires do, which is pretty amazing. That they'll take a beating and a lot of twisting and turning, but the insulation gives up first. Teflon is much more resilient to that type of mechanical stress and abrasion. The glass just wears out a little bit faster. Every time you bend it, it sheds a little bit and gets thinner and thinner and frays, and so it's not as nice to work with as the Teflon. But the process temperatures are up above 220 C. You have to use different insulation.
Yeah, that makes sense. So profilers have been around a long time, and from the first profiler ever made, I don't know if it was ECD or anyone else, but I would imagine it's probably you guys. The job of a profiler is to record temperature in kind of real time, right? That's kind of the main reason that they were invented. So that seems pretty basic, although I know there's way more behind the scenes than just recording the temperature, and plotting it on a chart. So what's changed over the last, since 1986 or so, since you made your first mole? What, besides the operating system and the various versions of, DOS and then Windows and whatever, what is the reason why these profilers can go into obsolescence and newer, more modern profilers are needed, besides the operating system and them just getting worn out or dropped too many times,
or burned up,
or burned up in the sacrificial mole, right? Exactly.
Yeah, exactly. So there are a couple of different things that force obsolescence. Some of it is manufacturability. As we know, these components are only available for a certain amount of time. We've had on our Supermole Gold, we kept that version of our profiler going for about 18 years. And the last few builds, I think we did, about 14 last time buys on components. And the builds got harder and harder and had more and more fallout. So there's a point of diminishing return on trying to keep old designs manufacturable. And so you get into a new design cycle because you're forced to, because of chip availability. And then every time you're forced to do a board spin, It's an opportunity to add features, add functionality, you know, faster, better, you know, better battery life or power management, the opportunity to increase logging speeds for different applications, to add different functionality. So the hardware itself is really based on manufacturability more than anything. Recording temperature from a thermocouple input, you're just measuring microvoltage and putting it into a log file. So it's not rocket science on the logger side. The real innovation and improvements usually come on the software side, and that has to come with usability of the software, making the complex more simple, being able to extract measurements from this time temperature plot in unique ways that are application specific. So semiconductor guy may want to do different measurements than a reflow guy, and we service a lot of different industries that have different types of measurements, like baking, for example. When you bake bread, for shelf life and different types of mouthfeel and bread quality, they have completely different measures, but we need to extract those from a time temperature plot. So being able to automate that is important. Creating software tools that save time. I know our prediction algorithm is a huge time saver when you're developing a recipe for a reflow profile. Instead of just making a small change and checking and making another small change and checking, we can use our algorithms and our software to accurately predict how those changes affect the profile, so you can get to that ideal profile in 1 to 2 runs instead of 10 or 12. Being able to automate recipe setup against multiple lines. So those are the types of things that we focus on in the software, and those are where those incremental improvements have come over the years. So you tie that in with the need to make something that's more manufacturable, and it's an organic improvement process that we go through, and we continually try to add value to our customers by putting in new features that help them save time or make it easier.
Yeah, that makes sense. How has miniaturization, and more specifically, bottom terminated components, landed in your industry? I can't think of a way to measure under a BTC in real time. And even just miniaturization, even if there is some clearance, parts are so close together. I mean, the components are a fraction of the size of the thermocouple these days. Yeah. So how does that present a challenge in your industry, and what has your industry done to respond to that challenge?
Yeah, that's an excellent question. The nice thing is, the smaller they get, the more thermally uniform they are. Thankfully, they heat up quick. So getting a thermocouple close is, you're getting a lot of data relevant to the assembly still. And we use smaller and smaller thermocouples. So, we're using 40 gauge thermocouples that are made with 0.003 of an inch wire to make these baby hair fine thermocouples that are more and more fragile. So that's always difficult. More of a challenge is the total process height. Physics is our enemy when it comes to protecting our electronics in these thermal processes. More people are trying to reduce their nitrogen consumption, so the clearances on ovens get smaller and smaller. Some of these processes are now even, say with some of the sintering processes, they're using acid environments that are particularly nasty to electronics and stainless steel, which we use a lot of to make our barriers. And so as these processes are developed and utilized, we have to continually try to work around protecting our instruments with insulation, and unfortunately, insulation technology hasn't really improved in the last 2 decades. So we have a minimum height that we can get to, which is about 3/4 of an inch. And if you have a clearance smaller than that, we're stuck. You're going to have to do the old-fashioned feed and retrieve method, which people hate.
What is that method? Explain what that method is.
Fishing, where you have, if you have a 16-foot oven, you use 17-foot long thermocouples, and you trail it behind, and when it exits the oven, you disconnect everything and pull it all through from the other side. so they don't burn up.
With gloves on. Yeah.
With gloves on, yeah. I mean, that's where traveling profilers really got their niche, is that people didn't want to use these long trailing thermocouples and pull them through the oven and burn their hands and melt connectors.
Profilers, what separates one from another?
I think there's probably three main parameters. One is, the brand. Do you know if you're going to buy something to record your process, is it going to last for 10 years? Is it well known? Is it going to be supported? So that all goes into brand. Obviously, we've been around for a number of years, and we're a known quantity. Our products last forever, to our detriment sometimes. We support those old moles as best we can still. We answer the phone. Customer support is obviously super important. If you have a problem, or more and more, it's coming into, do we get training? I've just been dropped into this position. I'm a new process engineer, and I don't know anything about wave solder, or I don't know anything about reflow. Can you give me 45 minutes and tell me the things I need to know? And we find ourselves doing that more and more, being the knowledge base for our customers rather than the measurement base. Used to be the solder guys who were the experts and would measure that, but anymore they more often come to us, and we provide that level of support to our customers. So that's a differentiator that you want to look at. And the software feature sets. We're very analytical in our software. So if you need unique extractions, if you like to do SPC, we're more on the engineering side of things. Some of our competitors are more on the ease of use and automation.
Do you consider ECD a software company that builds hardware to host the software, or a hardware company that builds software to allow it to work?
Well, that's an interesting question, because we are in a strange position. Our hardware, we sell to the electronics industry. Everybody knows how much it costs to build these things, and yet we charge a premium for our hardware, and you get the software for free. And that's the model that our industry has lived in for a long time. And people are starting to look at that. Do we want to do profiling as a service, and or software as a service, or give away the hardware and become a software company, open source the hardware? And so those are all interesting questions. There is a significant amount of risk and uncomfortableness around that. You and I were talking earlier about perceived risk on marketing and attending trade shows. The same thing is whenever you make a large change in your business model, there is some uncomfortableness around that. So at least for the near term, we're staying with the status quo, where we're a hardware company that makes really good software for free. In the future, we may become a software company that gives away their hardware.
Yeah. The reason I ask that is, I look at the Tesla model, auto manufacturer. Tesla they came out of the gate struggling to build cars with fit and finish. They had a wonderful technology. They were leading edge technology, but their cars, at least in the earlier days, weren't all that great. If you looked at the seam lines between panels, they were varying to great degrees, and they weren't building very efficiently. And then I read an article that kind of explained why, and it made a lot of sense to me. They are a software company building cars, or an engineering company, basically, an electronics company building cars, as opposed to Detroit, which was a mechanical car company, bringing in electronics. And so the mainstream car companies were late at evolutionizing the technology within their cars, but they knew how to build cars. So they just came at it from a different perspective. So that's what I was wondering. I'm sure that's the battle you guys, not so much the battle, but that's the fine line you guys are balancing since you started.
Yeah, absolutely. And the what's difficult is when we make a platform change, you can't give customers less than they had with the old version. right? So
Right.
it's always got to be more.
Right. Right. And
And
where does that
so,
end? Yeah.
yeah, exactly. And so your development cycles can get quite long, right? If it took you 3 years to develop for, Windows 98, when Windows 10 comes out, you got 3 years of development to get back to where you started, and then you got to add a little bit to get people to change.
Yeah.
So,
Right.
um,
Right. You have to. Yeah. Exactly. Do you drip out the expanded content, or do you just give it everything you've been working on? I mean, you got to hold something back for the next upgrade, right?
yeah, exactly. And like say, it's hard to come out if we made a hypothetically speaking, if we made a new application for our software to talk on an Android phone. How much functionality do you want to port into uh, a mobile device? Does it have to do everything that a desktop device does, or what's that 80/20 rule for the walk around version compared to the desktop version? So it's a tightrope. It's always interesting thought exercises. It also makes it incredibly difficult to nail down a scope and get things going on a software
Well, we talked
project.
earlier. I think we talked earlier about Microsoft coming up with new revs. Once you start making it iOS compatible, now that's another thing to break. When the next iPhone or Android phone gets an upgrade.
That's correct. There are some interesting things coming out from Microsoft. This is totally off topic, but they're coming out with a coding platform called MAUI, and it's the multi-user application interface. So you can develop on one platform, and you can bolt out iOS, Android, Windows software from that one build. So it's a very interesting build platform to work from. It's also bleeding edge, so it's not quite available yet.
Right.
So,
Well, knowing
that's
Microsoft,
the
that
risk.
even when they release it, it's not quite available yet. They tend
Right,
to
yeah,
do all their debugging in the field. That's just the nature of that company.
exactly.
Before we finish up, once an oven is set with its conveyor speed and zone temperatures, what causes it to produce different results? What is the mechanical reason why someone should buy a profiler? You can't just set it and forget it. Are there variables that change within the oven, within the infrastructure that's supporting the oven, within the boards where they will produce a different result from one day to another?
There's That's a really loaded question. There's literally hundreds of variables that can affect the reflow profile. So you have maintenance issues as far as potentially the exhaust stack pressures changing, um, the HVAC system, whether it's winter, summer. If you have a loading dock and people are rolling up the door for FedEx at 3 o'clock every day and letting in a bunch of hot air or cold air, you have internal processes inside the oven that may cause failures. Blowers can fail. Conveyor speeds can end up drifting over time. So there's literally hundreds of different variables that can affect the reflow profile. Even the power that you're getting from the utility can change the amount of available heat it is to recover when a board goes through, or board loading. We had one example where the company would run 20 boards and then they'd stop for 15 minutes, and then 20 more boards would come through. And the last 3 boards of every batch of 20 were colder than the rest because the first 17 boards sucked all the heat out of the oven and it couldn't recover fast enough. So there are variables that can affect the reflow profile. Uh, and you may not be able to catch them with single board pass profiling because you're collecting that data in the ideal time. The oven's stable, doesn't have any, um, you know, production load on it that may be varying the heat from the zones. And that's, we do continuous monitoring products that monitor that. Every 10 seconds we are taking a sample of the oven condition so that we can catch those variables as they happen. So if there are changes over time or immediate changes due to board loading or external maintenance issues or internal failures, that we can pick those up and let somebody know, set off the red flag that, hey, something in your process has changed. You should come check it out.
Yeah, that makes a lot of sense. What's the future hold for ECD?
Well, that's another loaded question. So Industry 4.0 is demanding automation. Closed loop control is always kind of the holy grail. So we can look at a board before it goes into the oven, select the best recipe for it, tell the oven, what temperature it should be at, and then send it through and know that it's been processed correctly. I think we're still a couple decades from that. But as we say, the sandboxes for oven manufacturers and profiling companies are definitely getting closer together. And having some type of closed loop control is probably the next step.
So something where the profiler can talk to the oven and basically say, hey, buddy, you need to slow down the conveyor, turn up this zone, or maybe even put the desired profile into the profiler rather than the oven, and then the profiler can talk to the oven. And is that kind of the strategy behind that, or the goal behind that?
Two-way communications is definitely on the roadmap. Let's just put it that way.
Cool. All right. Well, I don't want to tell you. Don't tell me so much where you have to kill me. So
yeah, exactly.
Yeah, I need to be around for another show.
Yeah, we are continually striving to make our profilers smarter and to do more and to make it easier for the operators. And so, being able to communicate and evaluate a profile is definitely on the roadmap. Excellent.
Well, Mark, thank you for spending the last about 45 minutes with me or so, and spreading your wisdom. I really appreciate it. You make me smarter, so I get to ask the dumb questions because I always have the smarter people on the other side of the screen. So thanks for enlightening me and educating me and my audience on the ins and outs of thermal profiling. I really appreciate it.
Yeah, no problem. Thanks for having me. Have a great day.
Thank you. You too. Thanks for listening or watching the Reliability Matters podcast. Be sure to subscribe to the podcast on your favorite podcast app, such as Apple Podcasts, Google Podcasts, Spotify, and so many more. Also, be sure to check out my other podcasts, including the Concept to Creation podcast, where I feature conversations with entrepreneurs within the electronic assembly space, and, as we discussed earlier at the beginning of the show, the Innovations in Technology podcast, where we discuss innovative products within our industry. All three shows are also available in video format. Check out the Reliability Matters or Concept to Creation or Innovations in Technology podcasts on YouTube. Just search the show's name and you can find all three shows. Or go to mikeconrad.com. That's Conrad with a K. All three shows also appear there. Again, thanks for being part of my podcast family. I appreciate you being here. Until next time, stay safe, stay healthy, and stay happy. And of course, keep doing it right. See you again soon.